Nossa, pô, entendi. Okay, good morning. So we'll continue with our study of angular momentum. Today we are discussing the conservation of angular momentum. Okay, so we discuss the conservation of angular momentum, which is a fundamental principle of physics, which states that the total angular momentum of a system remains constant if no external torque acts on that system. Okay, again, this is the rotational analog, if you like, of the conservation of linear momentum. Remember, for linear momentum to be conserved, that is to remain unchanged, we require that there is no external force acting on that system, so that the momentum of that system at any time is constant. So similarly, for conservation of angular momentum, we require that there is no external torque acting on the body or system. There is no net external torque, so that the angular momentum remains constant. Remember that the angular momentum is the product of the moment of inertia and the angular frequency. Okay, so for you to have a conservation of angular momentum, this product must remain constant. Of course, this means that if the moment of inertia, increases, then omega must compensate by decreasing, so that the product remains the same. Similarly, if it is that I is increasing, then omega will decrease, will be decreasing accordingly. Okay, so let's look at the basic objects that play the important role in conservation of angular momentum. These are what you already know. The angular velocity, that is your omega, which measures how fast an object rotates, or if it's pure circular motion, how fast it executes that circular motion, and it is measured in radians per second. Then the next one is your moment of inertia, I, okay, which is an object's resistance to changes in rotation, which is dependent on how the mass is distributed dependent on the mass and how it is distributed. If it is closer to the axis, of course, that means lower I. Remember that I is for a body or a point body, I is mr squared, where m is the mass and r is that position. Then we have the angular momentum, which, as we have seen many times, is the product of the moment of inertia and the angular frequency. Then finally, we have the torque, which is the rotational force, okay, the moment of the force, which is analogous to linear force that causes angular momentum to change. Okay. So how exactly does conservation of angular momentum work? Remember that the net torque acting on a system is measured as the rate of change of that system's angular momentum. That is, tau net is dl dt, where L is the total angular momentum of the given system. So, of course, if tau net, if there is no tau net, that is, if there is no net torque acting on your system, then the L dt will be zero. That is, the rate of change of the total angular momentum is zero, meaning that the total angular momentum is not changing, but is constant. Okay, so that's how conservation of angular momentum manifests. Once there is no net total torque, remember it is the torque that is responsible for the rotation. So once there is no net total torque, then the angular momentum of that system is conserved. Okay, and since L is I omega, another way of saying this is that I1 omega 1 equals I2 omega 2, where 1 and 2 refer to different times. So that the point is that the product of I and omega remains constant. So, like we noted earlier, if I decreases, meaning that the mass moves inward, okay? Remember, I is mr squared. Then omega must increase, okay? E.g., if you are talking about a skater, for example, who is pulling in his or her arms, then omega must increase to maintain a constant value for the I omega. Okay, so now I want to give the first code for this lecture. So the first code is 3QGAQ. 3QGAQ. All letters in capital. 3QGAQ. That is the first code. Maybe life. Okay, similarly, if I increases, then omega must decrease to compensate. So these are some examples in the real world where conservation of angular momentum is observed or seen. Like the case of the ice skater that we talked about. When the ice skater pulls his or her arms in, okay, that reduces the moment of inertia, his moment of inertia. So he will now have to spin faster. That is, omega must increase because I has reduced, okay, and vice versa. If it causes I to increase, then omega must reduce to compensate. So this is what makes skating possible. So similarly, a diver or a gymnast extends limbs so as to slow the rotations mid-air. So again, I and omega in this case will interact to compensate. So when omega reduces, okay, due to the slow rotations, then I will increase, okay, and vice versa. And our planets and stars too, which are formed from collapsing clouds, okay, so spinning faster as they shrink because when omega is is big, the moment of inertia will reduce, okay? And another example, a good one is bicycle wheels, okay? It is the angular momentum and the conservation of angular momentum that helps the bike to stay upright, okay? To maintain a constant product of the moment of inertia and the frequency of the wheel. Okay, so the next slide will look more closely at the heart's rotation. Okay, so the heart continues to spin due to the angular momentum it gained during the solar system's formation a long time ago. That is so, and although there are some tidal forces from the moon which provide a small external torque, okay, which is gradually slowing it down, okay. So I hope you know the implications of this, for example, for our planet, since the external torque is not entirely zero. So think about that. Think about what it means to the conservation of angular momentum of our planet. Okay, then like as noted earlier, in gymnastics and diving, conservation of angular momentum plays a very important role, okay? Although, of course, the individuals concerned may not even be conscious or aware of what is responsible for their for the possible things that they do. But that is the physics. So now, what is the scientific importance of all this? Now, there was a mathematician, a mathematical physicist, Emil Noether, a German mathematical physicist who lived until 1935, who established a very important theorem that anytime you have a system has some continuous symmetry, there is a conservation law associated with that symmetry. So you will learn this more, especially those of you that will be doing, those of you that are in physics or will be doing physics in your 300 or 400 level, you will learn more about this very important principle that due to Noether, that whenever there is symmetry, there is always a conservation law. So that basically the conservation of angular momentum arises due to the fact that the laws of physics do not change based on an object's orientation in space. Okay? So when an experiment is performed, for example, in Nigeria, it should be possible to reproduce that same experiment in Germany or in Ghana or in other places. So like I said, you will learn more about Noether's theorem in the future. Now let's take a couple of examples. So this is an example. You have a uniform rod. A uniform rod rotates in a horizontal plane about a vertical axis through one end. The rod is 6 meters long, weighs 10 newtons, and rotates at 240 revolutions per minute clockwise, okay, when seen from above. So we are to determine two things: the rotational inertia of the rod about the axis of rotation, and hence the angular momentum of the rod about that axis. Notice that in this case, this question is actually not about conservation of angular momentum, but about determining angular momentum itself. So you can take it as an example to illustrate our previous, what we discussed in our previous contact. So anyway, the mass of the rod is the weight divided by gravity, as you know, which is when you substitute the given values, the given value of the weight, and you use 9.8 meters per second squared as the value of acceleration due to gravity. Then you get 1.02 kilograms as the mass of the rod. Okay. Now we need the angular frequency in order to be able to determine the angular momentum of the rod about that axis. Remember that the angular momentum, L, is the product of the moment of inertia and the angular frequency. So from the information given, we merely need to convert 240 revolutions per minute to the SI unit of angular frequency. Okay, so 240 revolutions per minute. So one revolution is 2 pi radians. So that's why we are multiplying by 2 pi radians per revolution. Then 1 minute is 60 seconds. So that's why we are multiplying by 1 minute over 60 seconds. So when you do the calculation, when you press your calculator, you get 25.1 radians per second. So now that we know the angular frequency, we easily proceed to get the angular momentum, to determine the angular momentum of the rod. So this means that we need to determine first the rotational inertia, the moment of inertia. Okay. So the moment of inertia of this rod is given by 1 over 3 m L squared. Again, the moment of inertia will in general depend on the shape of your body. If it is just one body, one particle, okay? So for this rod, the moment of inertia is 1 over 3 times m times L squared. That is in general, we always, for simple objects, it will always be proportional to the product of the mass and the length squared, okay? So in this case, the mass is 1.02 kilograms and the length is 6 meters. So when you do the calculation, you obtain 12.2 kilograms meter squared as the moment of inertia of the rod. So we are now in a position to determine the angular momentum of the rotating rod, which is simply the product of the moment of inertia and the angular frequency. So when you do the multiplication, you get that. So now I call the second code for this class. So the second code is XUQNK, all capital letters. XUQNK. XUQNK. Okay, so let's take another example now. So the second example is, suppose that the sun runs out of nuclear fuel and suddenly collapses to form a white dwarf star. By the way, I hope that you know that the sun, our sun, is a star also. It's just one of the stars, one of the medium-sized stars in the Milky Way. That's the name of our solar system, okay? So the sun is just a star. Okay, so suppose that the sun runs out of nuclear fuel and suddenly collapses to form a white dwarf star with a diameter equal to that of the Earth. So assuming no mass loss, what will then be the sun's new rotation period? You know, since the configuration has changed, the period of rotation will also change. The present, that is this data, the known standard here is that the sun, the period of rotation for the sun is about 25 days. So at the end of this example, you'll be surprised how small compared to 25 days the new period will be if what we said happens. That is, if the sun suddenly runs out of nuclear fuel and collapses to form a white dwarf star. Okay. So in this case, notice that in this case, we have a conservation of angular momentum. That is the product of the initial moment of inertia and angular frequency will be the same as the product of the final omega I and omega F and IF, where F means final. Okay, so from data, let's compute the angular frequency, angular velocity of the sun. So that's, again, here you do a kind of conversion that we did the other time, okay? So one revolution in 25 days for 2 pi radians per revolution. Then 1 day is 86,400 seconds. So when you do the multiplication, that gives you omega, the angular velocity. Okay. So now that we know we need to know the moment of inertia so that we'll be able to determine the current angular momentum. Remember, that is what is going to be conserved. So we need to determine what it is now. Then we will use the fact that it will not change to determine the new thing. So for this sphere, for a perfect sphere, okay, the moment of inertia, remember I told you that it depends on the shape. In more advanced, this final expressions for the moment of inertia are always computed by performing an elongated summation, an integration. But you'll be doing that in your more advanced work in due course. So anyway, the moment of inertia of this uniform sphere is 2/5 mr squared, where m is the mass of the sun and r is the radius. So the initial angular momentum is therefore Li equals I omega I. So putting in the values, we have this. So we deliberately leave the m and ri there as is because we know that when we are doing the final, the m will still be there and also the 2/5. So there is no need. So they will eventually cancel out because we are going to have II and IF on both sides because of the LI, LF. So it is better to just leave the computation as this. That is without putting in the values for M and RI. So after the sun shrinks, it will now have a new radius, much smaller, okay? But the mass will still be the same because it is still the same sun, only that its radius has reduced because it has shrunk, okay? So the new moment of inertia will be 2/5 m rf squared. And so conservation of angular momentum then gives us that Li will be the same as Lf. So equating the Li there, remember for what we are actually looking for is the period of the rotation of the new sun, okay? And which we will be able to determine once we know the angular velocity, omega f, okay? So performing this equation and making omega f subject. So we have omega f is ri squared over rf squared. It's just a simple, very ordinary manipulation, the kind that we have been doing since secondary school. So you have this ratio, so you can see the mass has disappeared since it is the same mass. Anyway, and according to the data that we know, the present radius of the sun is 6.9610 times, okay, times 10 raised to power 8. So please correct this. There is an error here. A small one. Should be 6.96 times 10 raised to power 8, not 6.9610 times 10 raised to power 8. Okay. So similarly for the radius too, should be 6.37 times 10 raised power 6. So please insert the times. So you now have, putting in the values, you have your omega f being given by this. And you remember that your frequency is omega over 2 pi, and period, you did all this in the circular motion. And period is given by as the inverse of the frequency, so which is 2 pi over omega. And since you have calculated omega f, the rest is easy. So TF, that is the period of the new sun, is 2 pi over omega f, which gives you, when you substitute the values, approximately 3 minutes. So you can see if the picture that we painted actually happens, so that the sun shrinks, okay, to a much smaller radius, then it will take only 3 minutes for it to make one rotation. So you can see the significant difference compared to 25 days. Okay. I want to, at this time, I want to convey a message from your coordinator, okay, from the coordinator. The coordinator says you should do answer all the questions in chapter 4. That's your next tutorial. All the questions in chapter 4 of the booklet that you have with you. Okay. Now, I call the third code. So the third code is GQDYY. GQDYY, all capital letters. GQDYY. So I hope you got that. GQDYY. And that is the end of the class for today. Have a good day.